Okay, there we go. So here's where we were last time. We were talking about the chain rule, in particular the matrix form of the chain rule. We're going to see another form of the chain rule in just a few minutes here. But reminder, here's the matrix form of the chain rule. The big idea is that this matrix relates the x change vector to the y change vector. This matrix relates the y change vector to the z change vector. And so altogether then, how do you turn the x prime vector into the z prime vector? Well, you first apply the df matrix and then you apply the dg matrix. And altogether, that is what you do to turn the x prime vector directly into the z prime vector. So I think it's highly plausible when you think about it this way. Notice, thinking about it from a point of view of change vectors, and what are the matrices that relate those vectors. So we're not taking a coordinates point of view, we're taking a vectors point of view. Okay. All right. So we did an example last time. We did this special case, talked about something interesting that happens when there is a single sort of original input variable. And effectively you get parametric curves, namely that's a parametric curve. The derivative matrix is the velocity vector. Let's see here. That composition is another parametric curve. And this product derivative matrix is its velocity vector. And so what we have, again, just a reminder, is that the derivative of this function, this df matrix, is a relationship between input velocities and output velocities. In some sense, in this special case, the chain rule just recovers something we already knew. It's a restatement here. That what derivative matrices do is relate velocities. So, anyway, that's one special case, and we did the example last time. So picking up from there, here is another special case. It's a special case of that previous special case. It's the special case where not only do you have a single input variable, but furthermore, the eventual output is also scalar valued, just one output variable, in other words. So same story. I mean, we still have just the one input variable, and so this is, we already know that the derivative of this function is going to be a relationship between input velocity and output velocity. It's just that the derivative of that matrix now, well, there's only one single output variable. That means that there's only one row in that matrix. And so here we are again at this circumstance where, we're multiplying two matrices, but it's a row times a column, and that in fact is basically a dot product. Right? So that's really the only variation here. If you have a real valued, eventually real valued composition, then the derivative matrix can be reconceived as a dot product with the gradient. Okay. All right. So again, another example, but there's really nothing new in this example. But notice we have, let's see here, t as a function of x, y, and z. Right, and we've got the input x, y, z is described by being at that point 3, 2, 1 and moving with a certain given velocity. So the path of the bird is the input, and of course that's a function of a single variable. The way birds fly is its position as a function of time. Right? So this is that scenario. We've got a single input, we've got a single output. And so we know that we can compute the output rate with a dot product with the gradient. This gradient vector, how are we going to compute this gradient vector? Well, just straight out of the function, take the various partials, and we get this, and that. Those are the x, y, and z partials, respectively. And you plug in the point in question. Right, and that gradient vector turns into this, and that's what you dot with your velocity vector. Keep in mind our velocity vector given over here And so just like on the previous page, this is just gradient dot velocity gives rate of change of the function. What do you think? It's just a different kind of special case of the chain rule, but it's still the chain rule. All right. Oh, by the way, just real quick, I did make a recent change on this page. I had some arithmetic oopses on this page. So you may, if you have an older copy of the lecture notes for Chapter 2, you might want to discard and download the newer one where I had accidentally subtracted 3 minus 2 and got 2 for those exponents. I don't know what happened there. Anyway, it's fixed now. Okay. So now here's a different point of view on the chain rule. Again, we've, our point of view on the chain rule so far, and what I hope will kind of be your foundational point of view on the chain rule is this right here, that derivative matrices multiply because, well, that's what happens when you compose, when you multiply and then you multiply again, you're multiplying by a product. Again, we've already said the thing. But I think this is a very natural point of view on the chain rule. But sometimes you don't need to compute the entire derivative matrix. Sometimes you just want to know one element out of this. I just want to know a single partial derivative. Maybe I want to know the partial of z2 with respect to x1. Perhaps. That's just one element out of this product matrix. I don't want to have to compute the whole thing just so I can get one element out. So here's how we streamline it. We write down the matrix form of the chain rule. Notice I have the variables set up the way I have previously, where for the first function, the x variables go in, the y variables come out. For the second function, the y variables go in, the z variables come out. So we have that set up. The derivative matrices then are as I have written here. And again, instead of computing this whole thing, suppose I want to compute just one element. And, I compute that element by matrix multiplication. And in particular, the corresponding row of the left matrix dot the corresponding column of the right matrix. Now you can see that dot product showing up here and how I multiply this out. Just literally do the dot product and you get this right here. And so this single partial derivative I'm looking for, you can compute with that one. You might say simpler formula. I mean, there's no matrices involved in the way it's written here, and that may be appealing. Ultimately, there's probably less arithmetic involved here. That's appealing. But kind of a weirder formula, though. So pro-con, right? It doesn't have that natural feel that the matrix form has. Okay, so I do want to warn you one thing here. A lot of students get confused about the following. There's a temptation to say that, you can just, I can cancel. There's partial y1 up here, there's partial y1 down there, so those just cancel like we've been canceling numerator and denominator common factors since elementary school, right? Feels like you should be able to do that. You can't. That's not a thing in multivariable calculus. And I'm going to give you two reasons. One good reason, one not so good reason. The not so good reason is the easiest. If you were to do that in all of these terms, notice you'd get partial zi, partial xj a bunch of times. Right? So you'd get, on the right-hand side, you'd get m different copies of partial zi, partial xj, which is just not the right answer. So that's not good, right? Ultimately, that's not a good critique because what's wrong with reasoning is not whether it gets the right answer or the wrong answer. What's wrong with reasoning is whether it's valid or invalid reasoning. So what is the shortcoming in the reasoning is really what we should focus on, and here it is. You have to remember that this partial derivative is not a fraction. It's not a ratio of two independently existing, well-defined things. It's just not. This is part of a story. This is part of a scenario. In this scenario, we are viewing zi as a function of various y variables, and we're going to view y1 as being a variable, but then we're going to set all the other y variables to be constant, because that's how you do partial derivatives. So we set up this scenario where a bunch of variables are constant, one variable is a variable, and then given that scenario, then we look at and see how much zi changes. Now, by comparison, there's a completely different story going on in the factor on the right here. In this story on the right, again, we're taking a partial derivative. Again, let's see here, I'll use dark green. That means xj is to be thought of as a variable. All the other x's are constant. Fine. But what about the y's? And the thing is, the other y variables can't be constants. Can't be assumed to be constants. Because, check it out, xj is changing. And y1 is changing as a result of xj changing, but so are all the other y's. All the other y's are also functions of all the x variables. If you change the inputs, you should expect those variables to be changing. So, again, we've got two stories here. There's the blue story and there's the orange story. And these two things that you want to view as canceling are, they both represent how much is y1 changing, but as part of different stories. In different scenarios, different assumptions. They're not the same thing. So you just can't cancel them. It's not a thing. This is one of the really unfortunate things about the fraction-like notation for partial derivatives. It's a little too suggestive of something that isn't true. So heads up about that. And please don't step on this landmine. Don't make the mistake of thinking that you can just cancel these things or that you can just treat partial derivatives like fractions in general. It just doesn't work. Okay, what do you think? Is everybody okay with that? All right. Okay, so how do we make sense out of this equation that we wrote down previously? Again, here it is. There's I think, a really nice way of thinking about this. And here we go. Want to understand the partial of zi with respect to xj. There's zi. There's xj. I'm going to imagine that, well, now, of course, I'm holding all of these variables over here constant. And all of these variables here constant. All the other x's. And as I change xj, well, a lot of things are going to happen. As I change xj, y1 will change. Y2 will change, Y3, etc. Each one of those changes, though, in the y's, is going to make its own independent, parallel contribution to how much zi will change. Right? So you wiggle y1, that's going to contribute to a change in zi. But if you wiggle y2, likewise, that will contribute to a change in zi. And so will y3, etc., all the way on down the line. Right, so here's the way I like to think about this. I like to think about changes propagating along paths between the variables. So let's just take this one path at a time. This right here, that green path, represents that, look, when you change xj, then there's going to be some sort of corresponding change in y1. And how much more of a change in y1 is there than whatever change in xj? Well, that proportion is this partial derivative. So what I have in blue there, the amount that the change is magnified along that path is that factor. But then it goes along further. However much y1 changes, how much does that contribute to zi changing? Well, now this is, mind you, assuming, being interested only in the change of y1 and how much the change in y1 specifically is contributing to the change in zi. And so to understand this, I need to ignore changes in all the other variables. In other words, I want to hold these constant. In other words, I'm looking at the partial of zi with respect to y1, which is that factor right there. So what I think is a nice and satisfying point of view here is that this term in the multiplied out, sort of variable point of view on the chain rule, that term corresponds to this path between the variables in question. And then et cetera for the others. So you've got, of course, there's a bunch of other terms. There's a bunch of other paths between xj and zi. And then let's say the last one, for example, there's this path. And that gives you this term. And again, you can think it through that the, let's see here, I'm running out of colors. I will use yellow. We're going to have partial of ym with respect to xj. And then we're going to have, I think I really run out of colors here. I'll use gray. Partial of zi with respect to ym. Is that there? Yeah.
And this is kind of reminiscent of a neural network. So are neural network weights basically just like matrices of partial derivatives?
I have to plead ignorance. I'm afraid I don't have any previous familiarity with neural networks. Maybe. I wouldn't be surprised. Multivariable calculus comes up in a lot of places. Yeah. So that'd be worth looking into. I wish I had a better answer for you. Yeah. All right. Okay. So this is how I like to think about this equation. It comes out of matrix multiplication, but I like to think of it as sort of a consequence of thinking about these different paths. Again, each path corresponds to a term. By the way, said differently, notice each one of these paths corresponds to one of the, what you might call, intermediate variables. The variables that are kind of in the middle, right? Not the initial first variable, not the output of the output, right? But the ones in the middle here, these intermediate variables. Each path corresponds to an intermediate variable, and you can see that intermediate variable in the term that corresponds to that path as well. Right? So you can think of it as a path gives you a term. You can also think of it as an intermediate variable gives you a term. Okay. And you get one term for each intermediate variable. All right? Is that cool? All right. Okay. So let's see an example of this. Here we go. I've got various x variables. Then I've got this function f that turns x variables into y variables by way of that function there. And then I've got g that turns the y variables into z variables given by this function here. Okay. Now, I'm a big believer in having a diagram representing all of your variables and which ones are kind of, grouped together and inputs or outputs from the same function and which ones vary, which ones depend on which one. So I summarize all of the above like this. And you can see here we have the y's are functions of x1, x2, and x3. And that's what this represents. And then the z's are functions of y1 and y2. That's what that represents. So kind of sometimes I call it the road map of relating the variables. And now with that in mind, look at the question we've been asked. We've been asked to compute the partial of z2, there it is, with respect to x2. There that is. And now we can start writing down intermediate variables, aka paths, writing down the corresponding terms, and we get ourselves a little chain rule here. So specifically, we have what you might call the y1 path, thus giving us what you might call the y1 term. Everybody good? Then we have a y2 path y2 being the intermediate variable, and we get a y2 term in our chain rule. And so altogether, the partial of z2 with respect to x2, there it is. Now, if you were to take the matrix point of view on this, all right, then you'd have a matrix representing the g function, and then you'd have a matrix representing the f function. Each would have 6 elements, and you'd have to multiply, and then you get a bunch of stuff you don't need. This is just pulling out that one formula, that one expression, that one element of that product that we actually want. Yeah?
Can you explain why the only intermediates are y1 and y2?
Yeah, well, that's right, because looking at the diagram, these are my sort of initial variables, my original inputs, right? You might call them. These are my eventual outputs in the composition. And what we mean by intermediate variable is variables that are kind of in between. They're the outputs from the first function that we're composing, aka they're the inputs to the second function that we're composing. And thus the name intermediate. Is that cool?
Yeah.
Okay. Yeah. All right. So 2 intermediate variables, so 2 terms. Yeah. Then it's all details. Now you do have to compute appropriate partials. Let's look at one of these. Let's look at the partial of z2 with respect to y1. Don't forget what z2 is. z2 is the second output from that second function. So z2 is that. It's y1 cubed. Right? So we're taking then the partial of y1 cubed with respect to y1, and that gives us 3y1 squared. Everybody good? So in each one of these 4 factors down here, you need to identify, wait a minute, what is this thing that I'm taking the partial of? It's going to come from one of the above functions, interpret it appropriately, and take partial with respect to what it says, and there you go. Okay. All right. Okay, heads up about one thing. Please be careful not to confuse your variables. I'm going to start off by showing you a single variable example of confusion of variables. I know you all know single variable calculus. Again, the purpose of this is to segue, provide an analogy, a basis for comparison, so we can see what it looks like in the multivariable case. Okay, single variable calculus. There's a function. Nothing wrong with it. Here's a function. Nothing wrong with it. Two perfectly good functions. Right up until the point where the question asks me to compose them, and then other things follow, namely taking a derivative. But the very moment that I want to compose them, I've got a confusion of variables problem. Now let me show you what can go wrong with this confusion of variables as it is. We can kind of fast and loose write down that the derivative of a composition is the product of the derivatives, right? It's kind of true. Suitably interpreted. Anyway, I've written it down a little bit carelessly. And these are easy derivatives to take. What is g prime? I want to take the derivative of x cubed. Great, that's 3x squared. What is the derivative of f? What is f? The derivative of x squared is 2x. And you can multiply that out, and you get 6x cubed, which of course is wrong. The composition is, of course, obviously x to the 6th, and the derivative should be 6x to the 5th. Now, where did I make a mistake? A couple different points of view. The Newton take on this is that don't forget your g prime is supposed to be evaluated at f of x, not at x itself, right? And so we have to evaluate that g prime function at f of x, which is x squared. And you stick that in there, and all of a sudden the 3 times the thing squared, but the thing is no longer x. Now it's x squared that's being squared. And the algebra works out, and you get the right answer. And that's a take that you can make. I think, though, it's just easier to avoid confusion of variables in the first place. Just set yourself up to where making mistakes just isn't even possible. Much more natural. So again, I claim that the very moment that the question says, hey, I want to compose these, we should be thinking, oh, I want to compose? Okay, well, whoa, slow down then. We've got to, you're saying f is a function of x, so I really need x to be that input variable. Then whatever I put here, whatever I call the output from f, that had better be the input to G. And right now the input to G is set up as also being X. And so as it stands, I've got X here in addition to here. Now X is playing both the input and the output of F. Well, that's just confusing at best. So change it. It's so easy to do. We can, anytime we want, take a function and just write it in terms of a different dummy variable. Now, nothing happened here, right? This says, whatever you give to me, I'm going to cube it. This says, whatever you give to me, I'm going to cube it. It's the same function. It's just, okay, sure, it's written in terms of, here, the something that you're going to give me, I'm momentarily calling X. Here, I'm momentarily calling it Y. Doesn't matter what you momentarily call it. It's the same function. But if you write it this way, then we don't have a confusion of variables problem, right? F is a function of X. G is a function of Y, meaning that the output from F is no longer going by the same name as the input to F, and there's just no issue. There's no confusion left. And at this point, be as careless and sloppy as you like in terms of how you write down the chain rule. Here it is. Chain rule, right? Derivative of composition is the product of the derivatives. Fine. Let's see. G prime, derivative of y cubed is 3y squared. I'm not worried about where I'm evaluating it. Whatever. Y, I guess. Take the derivative. The notation will keep track of that for you, right? What's the derivative of f? Derivative of x squared is 2x. Multiply those out. You get that. And then again, don't forget what y is. Y is, well, it's the input to G, and that means that it's the output from f. Y is x squared. And plugging this into there gives you the right answer. I meant to do that in purple. There we go. Is that cool? Everybody see? So just avoid the confusion of variables in the first place, and there is no problem to be worried about. Okay, so that's single variable. Again, I hope that is familiar and satisfying. We get the exact same problem with multivariable. So here's a multivariable function. Nothing wrong with it. It's fine. Here's another multivariable function. Not a thing wrong with it. Perfectly fine as written. Until we say something about wanting to compose them. And as soon as you want to compose them, we got a problem. Because we already said that I want f to be in terms of x and y. Okay, so what are we gonna call these outputs here? Well, the outputs, I better not call them x and y. I can't call the outputs x and y if the inputs were x and y. I better call these outputs something else, maybe u and v, and whatever those outputs are have to be the inputs to G. So we just need to rewrite G, same exact function. Just instead of in terms of dummy variables x and y, now they're in terms of dummy variables u and v. Otherwise identical as function. And now, again, be as careless and sloppy as you like when you're writing down the chain rule. No problem. The notation will keep track of things for us. Here's the derivative matrix for f. Here's the derivative matrix for g. I just took the appropriate partials. I'm not keeping track of, wait a minute, where am I evaluating this? No, it's going to automatically take care of itself. There's df, there's dg. Again, we're interested in the composition. Derivative of the composition is the product of the individual derivatives. Do be careful about which one's on the left, which one's on the right. We actually have dg on the left here, df on the right, because f acts first. Right? And this is all fine. No problem. Except I suppose, if you think about it, the composition G composed F, let me do this in purple. This composition G composed F is this function. The composition is a function of X and Y. I probably really ought to write the derivative also then in terms of X and Y. And that means that I'm going to need to write, I'm going to have to figure out how to write V in terms of X and Y. Where am I going to get V as a function of X and Y? Well, don't forget what the diagram tells you. V, being as it is the second input to the G function, it is also the second output from the F function. And there it is. V is X squared minus Y squared. V is X squared minus Y squared. Does that make sense to everybody? Okay. And then likewise for U, let's see, I'm going to have to figure out what this U is. What is that U right there? Well, U is the second, it's the first input to the G function. That means it is the first output from the F function, and again here it is X squared plus Y squared, and so U like that. How we doing? Everybody happy? And then you just multiply these matrices. All right. Yeah. So next thing I want to talk about is second derivatives. A quick reminder, this part's not in the book. I think it's weird that the book doesn't include that. I think this is really important. I'm going to show you a physics example after we're done with this. I think is really important. Anyway, ultimately, in that physics example, this is critical to making it work. How to take second derivatives with the chain rule. So I'm just going to dive in and get started on the process. I am, however, real quick, for dramatic purposes, I'm going to scratch this out. We'll unscratch it in a minute, but for the moment, don't look at this. And let's just see what we've got. We've got Z as a function of X and Y. Fine, represented on our diagram. R and theta are the usual polar coordinates. Polar coordinates means X and Y are the usual functions of R and theta. We add that to our diagram. And you see now we have a composition. Z is a function of intermediate variables X and Y, which are themselves functions of R and theta. Composition, right for chain rule. Okay. So we have been asked now to compute the, let's see here, I'll do it like this, the second partial of Z with respect to R. That says that I'm going to look at the composition where I think of Z as being a function of R and theta in composition. I'm going to hold theta constant, treat theta as a constant for this whole conversation. And having done so, I want to then use the chain rule and figure out how to take the derivatives of, let's see, Z with respect to R. And the first partial is easy. Partial of Z with respect to R, there's an intermediate variable X, giving us an X term. There is an intermediate variable Y, giving us a Y term. And boom, there you go. First partial is immediate use of the chain rule. And then a little bit of sort of notational convenience. Let's not forget that an alternative notation for a partial derivative is to use subscripts. It's just notation, right? Nothing really happened there. Sometimes, and this is one of those times, it is more convenient and satisfying somehow to write this as Zx than it is to write it as a fraction. Okay, likewise there. And then, of course, don't forget, we know what the partial of X with respect to R is. X is a known function of R and theta, right? This the way that x depends on r and theta, well, it's r cosine theta. We know it exactly. And so that's an easy partial to write down, and likewise for y. Okay, so what to do next? We just got through computing partial of z with respect to r. I want to know the second partial. That means I want to take the r partial of the r partial I've just computed, and I want to see what that is. Everybody with me? Okay. And we're going to go slowly and carefully through this one. There's some tricky curves. First thing to realize, don't forget theta is a constant, right? And therefore cosine theta and sine theta are constants. Because we're taking partials with respect to r. R is our only variable at this stage, right? And so theta is held constant. We get to treat it like a constant. Constants factor out, so we get that. Is that cool? Everybody good? Didn't really do much there. Here's where it gets weird. And that's the question of what to do with this. Let me pick a different color here. What to do with r partial of zx. And I'm going to show you the wrong thing first. I'm going to show you what a lot of students mistakenly think, and I understand where the point of view comes up on this. But what I'm about to show you is wrong. It's really wrong. So here it comes. It's tempting to just call this ZXR. Right? You can see why students would want to do this. We had ZX, R partial. Well, partial means subscript, so just put the subscript over on the right. Seems like a reasonable thing to want to do. And it's importantly, dramatically wrong. Let me explain why. When we write down this, when we talk about partial derivatives, right, we talk about, you're going to view the function as a function of just the one variable and hold all the other variables constant. Okay, well, what is, for example, z a function of? There's two different ways you can think about it. You can think of z as being a function of x and y. And with z thought of as a function of x and y, you can talk about the partial with respect to x. That would mean holding y constant, and that gives you partial of z with respect to x, which is this, which you can write like that. That's all fine. Okay. Importantly, at the start of all of that, we have that z is a function of x and y. Now, on the other hand, I can view z as being a function of the composition, right? That it's the output from a composition, the inputs to which are r and theta. And we could talk about theta being constant, and talking about partial of z with respect to r. And that's all fine. What you can't do is view z as being a function of kind of all of them. This is not. You can't, that's not, these are not independent variables. Right? X and y are independent of each other. You could talk about holding one constant, changing the other one, doing whatever you want with any of them. You can't do that with these. So, for example, if this is how I was viewing z as a function, as literally as a function of 4 input variables, the partial with respect to r, you would have to interpret as holding all 3 of the other variables constant as you change r. And I claim this isn't possible. Right? You change r, you're changing x and y. They are functions of r. So this is just garbage. You cannot view z as a function of all these inputs. And when you write something like ZXR, that's what you're implicitly kind of suggesting, is that x and r are both inputs to the function that gives z. And they aren't. So this is garbage. Please make sure not to interpret this thing here correspondingly. It's just not It's not that it's not right. It's not even meaningful. It's just garbage. Does that make sense to everybody? Okay, so now, if we can't do that, what do we do? How do we deal with this? And there's a great answer to this question, and that is to make an appropriate interpretation of what ZX, I don't know why that keeps getting into that mode, what ZX is. And here's where I'm going to come up to the top of the page here. We've previously noted that if you have a function of x and y, then so are its partials. Right? If you have some expression involving x's and y's and you take an x partial, you get a different expression in terms of x's and y's. So ZX is a function of x and y. That's what ZX is. And I'm going to represent it as such. There it is. ZX is a function of x and y. I'm appending that to my diagram. Previously, it wasn't even on the diagram. But now that we've got this thing, ZX is in our work. We need to see where it is on the diagram so we can see how it participates and how it might connect to other things. So I'm appending the diagram. And then likewise, this ZY thing. What is ZY? Well, it's also a function of x and y, just like Z was. So ZY, also a function of x and y. And with our new appended diagram, now it's just a matter of just writing down the chain rule the same way we would any other sort of a situation. And so here we go. Let's write down the chain rule here for partial of ZX with respect to R. Well, there's ZX. There's R. They're separated by some intermediate variables. And so, okay, well, there's the first intermediate variable, aka the first path is through X. And here is our X term. And then here is the second path. Oh, whoops, I missed. Second path from R to ZX. Intermediate variable Y. There's that second term. And so this partial here, this partial of ZX with respect to R, by way of the chain rule, two terms, one for each intermediate variable. We've got the green term, we've got the blue term, and that's what that partial is. Chain rule just tells us. And of course, don't forget to bring along. We've got this cosine theta. That's a constant that sticks around for the ride, as constants do. What do you think? Everybody see how that's ultimately just straight up chain rule, right? We're just applying the chain rule, the intermediate variables version of the chain rule, just like we would in any other case. Yes.
Explain how you got the cosine and the sine in the initial
Oh
derivative.
yeah. So like where this came from? Yeah. Okay. So where it came from up here. So this cosine theta, what it was is it's literally the R partial of X. And because so if you think back to polar coordinates, this is the standard polar coordinates. X is R cosine theta. You take the R partial, it's cosine theta. Yep. Okay. All right. So likewise, for the next term, and again, slowly and carefully, we want to take the partial, it seems, of ZY. There it is. With respect to R. There it is. Again, we have two paths, aka two intermediate variables. There's the X path. There's the Y path. And thus X and Y terms. And therefore, the chain rule gives us that. This constant sine theta sticks around again, as it will do. And there you go. Everybody good? Okay. So the big theme, there's a couple of big takeaways from this, and that is when you're doing second partials with the chain rule, make sure that you interpret very carefully and correctly what's a function of what, and represent as such on the diagram. And then don't try to do too much too fast. Take it nice and slow. It'd be tempting to take this constant and, try to factor it out and also in the same step, try to start working on that partial derivative right there, all in one step. That's too much, too fast. So just take it nice and slow, so that when the time comes and you need to compute one of these partials, that you can just focus in on that and only that, see what the intermediate variables are, and write down your terms accordingly. So slowly and carefully, make sure to always keep track of what's a function of what, and it'll go through. Okay, and then there's some wrap-up details here at the bottom. Here we have partial of zx with respect to x. Now, again, let's slowly and carefully, again, I can view zx as being function of x and y. I can also, though, just remind myself, z is a function of x and y. And what this says right here is I'm going to take that z, I'm going to take its x partial. Fine, there's no chain rule involved in that. And then I'm going to take the x partial of that. Fine. Again, no chain rule involved. This is literally just zxx. So that's an easy rewrite. Nothing to be done there. No intermediate variables to be worried about. Again, you have some easy trig from polar coordinates. And once you have all these terms written out, you can multiply and collect, and here's your final answer. Okay, now let me show you what this is good for. Among other applications, this is just the first one that came to my mind. Y'all have already seen a homework exercise about the Laplacian. And the homework exercise that y'all have seen pertain to the heat equation, right? How heat moves. But FYI, the Laplacian is also very important to understanding what we call the wave equation, how waves flow, and how electrons behave, and how gravity works. There's a bunch of stuff that depends very strongly on the Laplacian. Okay, so here's the formula for it. In rectangular coordinates, because my partials are with respect to the rectangular variables. And here's the problem. Problem is that this f that we want to apply the Laplacian to, very often it's more natural in spherical coordinates. And you can't take rectangular partials of a spherical function. It's the mismatch, and it's weird. So here's the idea. You can just rewrite the Laplacian. And I know it looks unappetizing, but there you go. There's what we call the spherical Laplacian. It's the same as this, just in spherical coordinates instead. This is something y'all can prove on your own. I'm not saying you should. There's a lot of details in this calculation. But look at what you would have to do this. One of the things you'd have to compute is this right here, the theta second partial. Well, here's f, here's theta. There's intermediate variables x, y, and z, and you can play the same game that we played on the previous page and compute this second partial by taking the first partial, realizing you created several new variables, documenting those on the diagram, taking the next partial, keeping track of when to use the chain rule based on your diagram, etc., just like on the previous page. And you can then also compute the phi partial, which you then multiply by sine phi. And then you can take the phi partial of that, and et cetera, et cetera. You can compute all of these things, and when you combine them like this, believe it or not, and again, it is quite tedious, you get the rectangular Laplacian. So, what is this good for, you may ask? Well, check out the following example. Suppose we want to understand gravitational field of a single point mass. And by the way, this could just as well be understood if we're thinking about a single point charge and the corresponding electric field and the corresponding electric potential. So whichever metaphor you like, it doesn't matter. Those potential functions obey this rule. It's called the Laplace equation. So we need to find a function whose Laplacian is 0. Said differently, I'm going to need to find a function and then compute its Laplacian. I'm going to have to take this function and do the Laplacian operator to it. So here's your choices then. One choice is to take the rectangular formula for this function and apply the rectangular Laplacian and punch that up. And you're taking various partials of, there's your expression, and you can already see this coming. That's going to be super annoying, right? Because, there's fractions and denominators and square roots and more fractions because the exponent's a fraction. Oh my God, what a pain. Right? You can do it, but it's a pain. Here's your alternative. You can use same function, but written in spherical form, and use the spherical Laplacian, and you can compute this instead. Now, again, take your choice. Which one do you want to do? There's a temptation to look at that and say, well, it looks shorter, so maybe that's easier. But this one's a pain. I'm going to do this computation for you right now, and it's going to take me about 30 seconds. Because this very first derivative that I have to do here, I have to take the theta partial of an expression that doesn't have any thetas in it. That's 0. This whole term goes away. Next, I need to take a phi partial of a term that doesn't have any phis in it. So all of that ugliness, poof, disappears in a puff of smoke. Everybody with me so far? And just real quick before we finish this up, just real quick, how did we get this lucky? We got this lucky because the function that we're interested in here is naturally written in spherical coordinates, right? The way a charged particle creates electric potential naturally should depend on distance from where that charged particle is. Rho is just kind of fundamentally how it should be written, and x and y and z are weird coordinates. And if you're thinking about things that naturally depend on distance. So it's to be expected that things would work out nicely in spherical coordinates. The function is naturally spherical. The last little bit is super quick. The rho partial here is not 0. You get negative k over rho squared. That rho squared in the denominator cancels with this rho squared right here, leaving us with just negative k. The rho partial of a constant negative k is 0, and this whole thing goes away as well. And so grand total, this adds up to 0, as it should. And that was a super easy calculation, way easier than the alternative. Okay, so anyway, ultimately all of this is an application of this business here about second partials in the chain rule. Okay, y'all have a good day. See you later. Quick reminder, don't forget we have an exam on Monday. Right? Coming up real quick here. So heads up. And real quick, we did finish 2.5. So I'm going to be filling in this cell right here to say 2.5, because that's what we finished today. The green, which again will include 2.5, is what's fair game for the exam. Good luck.